Hey guys, welcome to our review video for our test tomorrow. I'm going to be going through the answers to your practice quiz that you took today, and so feel free to fast forward to the questions that you were struggling on to see the answers. The first question asks us to explain the role of metals and of nonmetals in an ionic bond. So before going any further, let's just review where the metals are. Metals are on the left side of the periodic table, right? They're groups 1, 2, and 13. And so anything in group 1, 2, and 13 have 1, 2, and 3 valence electrons, right? So they look like this. Oops, what's happening? They look like this. They've got the X with a dot, the X with 2 dots, or the X with 3 dots. So since they don't have many valence electrons, they don't have many dots, what they do, what their role is to always give away those valence electrons, right? So when they give those away to other atoms, other elements, they end up with a charge, right? And they become positively charged because they give stuff away. So metals lose or give away electrons and they get a positive charge. Nonmetals are anything in group pretty much 15, 16, and 17. They have a lot of dots. So for example, something in group 16 has 1, 2, 3, 4, 5, 6 dots. And so all it needs is 2 more dots to have a full 8, right? And so nonmetals typically steal their electrons. So now that we know basically the role of a metal is to give away electrons, and the role of the nonmetals are to gain electrons or steal them, we need to use these terms in our explanation. It's really easy to use the terms electrons because we can talk about how nonmetals have a lot of electrons and they just want a few more. And we could talk about how metals have only a few electrons, so they want to give them away. But how do we use the term octet rule? Excuse me, bless me. Okay, octet rule is the rule of getting 8. So nonmetals want to fulfill that octet rule by stealing electrons to have a full 8, or fulfilling the octet. So we can use that in our term. And then the noble gases, remember, they have a full octet, they have a full 8. So we can talk about how metals lose electrons to be stable. And we can say nonmetals steal electrons to fulfill that octet rule and to have 8 electrons like the noble gases. Okay, question 2 says name the bond that exists between B, E, and S. In order to know what bond exists, I need to know whether these elements are metals or nonmetals. And so I look on my chart, and beryllium is in group 2, so it's considered a metal. Sulfur is in group 16, so it's considered a nonmetal. And the staircase is our separation. It's the separation between metals and nonmetals. So anything to the left of the staircase is a metal. So if this is our periodic table here, here's the staircase. These are all metals. These are all nonmetals. Okay. So anytime you have a metal and a nonmetal, it's an ionic bond. Okay. So whenever we're mixing these two together, it's ionic. Whenever you only have nonmetals, it's covalent. Whenever you only have metals, it's metallic. So if we had to explain why we knew what type of bond it was, we would just say ionic bonds are anything between a metal and a nonmetal. Question 3 is the same question. It's asking what bond exists here. Well, sulfur is in the nonmetal section. And so 2 sulfurs means that this is a covalent bond. And we would say why? We would say covalents are 2 or more nonmetals bonded together. Okay. All right, this next question is asking us to identify polar ionic, polar covalent. Hold on, I did something weird. Polar ionic, polar covalent, and nonpolar covalent. So in order to do that, I need to know what these definitions are. Polar ionic is just essentially it's ionic. It's when you have a metal with a nonmetal, okay? Polar covalent is just when you have one nonmetal, nonmetal A, mixed with another nonmetal that's different, so nonmetal B. Nonpolar covalent, however, is when you have two of the same nonmetal. So nonmetal A with nonmetal A. The exact same nonmetal is called nonpolar. Two different nonmetals is called polar covalent. So circle the compound that's polar ionic. The only one that has a metal and a nonmetal is lithium chloride, so that's one that's polar ionic. The ones that are nonpolar covalent have the same exact nonmetal. So all of these here, it says put a box, okay. All of these have the exact same set of elements here. Okay, so all of them are nonpolar covalent. We don't have any that are polar covalent because polar covalent would be two different nonmetals put together. Okay, next question says circle the compounds that conduct electricity and put a check next to the compounds that are malleable and ductile. When you're reading this question, what you might think is, well, I don't even know what these compounds are. How do I know whether they conduct electricity or not? Well, let's think about what we know about electricity. Okay, we know from our notes that ionic compounds have a metal in them, right? And metallic compounds also are made of only metals. Ionic and metallic are the only two bonds that have metals in them. Anything that has a metal can conduct electricity. So we just have to find the compounds that are ionic and metallic. Hydrogen is a nonmetal. Sulfur is a nonmetal, so this is covalent. Magnesium is a metal. Chlorine is a nonmetal, so this is ionic. Au is a metal. Ag is a metal, so this is metallic. So I'm going to circle MgCl2 and AuAg because those are the two that can conduct electricity. Then it says put a check next to the compounds that are malleable and ductile. Again, from our notes, we learned the only type of compound that's malleable are metallic bonds. So I'm going to put a check next to the metallic bond because that's the only one that would work. Now it's asking me which family will never react with another atom to attain a stable configuration. What's the one group, the one family that we learned never, ever, ever reacts with anything? That's your noble gases. The reason why is because the noble gases have a full 8 set of electrons, so they never ever want to react with anything else to get more or to lose any. Question 7 is pretty straightforward. It's asking about metals and nonmetals, and we kind of talked about this earlier. Metals, we know that they give away electrons, and nonmetals steal, right? So I'm going to put a 1 here next to give away electrons because that goes with metals, and a 2 here because nonmetals steal. When electrons are given away, what charge do metals get? Well, when you lose electrons, when you're giving something away, it's positive charge. When you're stealing, it's a negative charge. We learned that positive charges go with cations. So the metal is a cation. So I'm going to put a 1 there. The negative charge goes with anions, right? And so nonmetals are anions. So we're going to put a 2 there. These next few ask me to draw the structures. And so the first two asked me to draw ionic compounds because it's asking for an electron dot transfer. So here I drew, anytime it's electron dot, you draw the arrows, the brackets, and the charges, okay? So strontium, let me look at my hand and nanoPeriodic table. Strontium is in group 2, so it's got 2 dots, 1, 2. Francium, oh, that's not francium, sorry. Fluorine is in group 17, so it's got 7 dots. And it says 2, so that means I have to draw 2 fluorines. So here are my fluorines. And remember that anything that is already paired up is basically in a long-term relationship. It's not going to react with anything. So you got to look at the bond, the single electrons, because those are the ones that bond. So this one electron is going to bond with the 1 electron in fluorine, but instead of drawing a line, I'm going to draw an arrow because fluorine will totally steal that electron from strontium. And then I'm going to draw an arrow to this fluorine because this fluorine will totally steal the other electron from strontium. After I've drawn the arrows, I have to draw brackets. So my brackets around strontium would show a +2 charge because it lost 2 electrons, and then my brackets around fluorine would show -1 charges because they each individually stole 1 electron.
Pardon this interruption. Mrs. Stork and Mr. Halford, please report to the counseling center. Mrs. Stork and Mr. Halford, please report.
Anyway, moving on. The correct electron dot transfer for cesium astatine. So cesium is in group 1, so it has 1 dot. Astatine is in group 17, so it's got 7 dots. So remember, these aren't going to bond with anything because they're already paired up. And since it's ionic, we're going to draw an arrow showing that cesium's atoms or electron is totally stolen by astatines. So cesium has a +1 charge because it gave away an electron, and astatine has a -1 charge because it stole an electron. Now we're going to draw Lewis structures. And so how is that different? Lewis structures, we draw the bonds. We're going to draw just a line showing that the electrons are being shared. So we do that for Lewis structures. So again, I'm going to draw my H with 1 dot because it's in group 1. My chlorine is going to have 7 dots because it's in group 7. And sorry, my dots are kind of wonky. Again, the ones that are paired are never ever going to react. These are the two right here. These are going to be the two that are going to react together because they are single and they are so ready to mingle. Now here's what a lot of y'all do when you're drawing the bonds. You're going to draw that. That is not an accurate bond because I still see the 2 dots. These dots need to be enveloped. They are part of the bond, so you should not see the dots anymore. Now notice this isn't an arrow. I'm not showing hydrogen's electron going to chlorine. They're actually both sharing the electron. So there's no charges and there's no brackets. This is an example of a linear model because I have 2 atoms, so it forms a line. Now I'm going to draw the Lewis structure for CO2. I have 3 atoms, so I have to figure which one's going to go in the middle. You always draw the atom that has the most opportunities to bond in the middle. Carbon has 4 dots and all of them are single, so it can bond to every single one of those dots. Oxygen, however, has 1, 2, 3, 4, 5, 6. These are already paired. These are already paired. It only has 2 opportunities to bond. So it's going to bond once here and once here. My other oxygen I put on the other side, and I go 1, 2, 3, 4, 5, 6. These are already paired up, so they cannot bond. But these single ones are the ones that will bond. So I'll have a bond here and a bond here. Because this looks messy, I always redraw it to show the bonds not being at weird angles. So I would draw O. These are the dots that are already paired. And then I draw 2 lines to indicate those 2 bonds to carbon. And then my other oxygen, I draw my single dots.
Wildcat staff, just a reminder, we will be meeting in the main cafeteria beginning at 7:15. Thank you.
Showing these double dots. And again, this is linear because it's in a line. Okay, my last few questions are asking about the VSEPR shapes. So those are the tetrahedral and trigonal planar shapes. Since we aren't drawing out the compounds, you have to think about how many atoms there are. There are 3 atoms in CO2, and we know that anything that has 2 to 3 atoms will be linear unless it's water, right? Water's bent. So this will be linear. And the next question is water, and water is always the bent shape, which looks like this. Now, this one has 5 atoms, and we've learned that 5 atoms form a tetrahedral shape. So that's the answer for this one. Next, it's asking questions basically about our previous unit, Unit 5, and it's asking about then family name that Group A is in. Anything in Group 1 are called the alkali metals. Group 2 are called the alkali earth metals, and then these are our transition metals. Group 17 are the halogens, and group 18 are the noble gases. So you'll want to remember all of those names for the test. Now it's asking me about ionization energy. So one thing you need to remember from our previous unit are the way the trends go. So we know ionization energy and electronegativity both go the same way. They go up and to the right towards helium. The other two, the radius trends, ionic and atomic radius, they go the opposite, to the left and down towards radon. Okay. So which element has the greatest ionization energy? If we go up and to the left, D has the greatest ionization energy. The least electronegativity, or the least electronegative, would be A, because electronegativity goes up and to the right. So D is the greatest. So what's the opposite of D? That would be A. Then it says, which element has the largest atomic radius? Atomic radius goes to the left and down, so A, again, would be our answer. Here's our last question. Circle all the true statements. Okay, do nonmetals steal from metals to obtain a noble gas configuration? Yes, they do. Nonmetals have a lot of dots, right? And so they want to steal. Metals only have a few dots, so they want to give away. Group 2 elements will react to gain 2 electrons. Okay, group 2 elements have 2 dots. They give them away. They do not gain. Okay, so that's not true. Group 17 elements will react to gain 1 electron. Let's see. They have 7 dots. Do they need 1 more? Yes, so C is correct. Then metals, do they lose electrons? We just talked about how metals lose electrons. And do the nonmetals get those electrons? Yes, to obtain noble gas configuration, meaning to obtain 8. We know nonmetals steal to get 8, so that's also true. And that is it. So good luck in studying for your exam, and I will see you tomorrow.